back on to the Carr Rambler. So if you remember, this one's come in for a service, and it's got a couple of issues that the customer wanted to sort out. The main issue is that the amplifier hums in triode mode, but not in pentode mode. So let's see if we can work out what the cause is. Now, first thing to do, normally if you get a hum in the output stage, it could be a mismatched set of valves, as in they're not closely matched to each other. And that hum becomes more apparent in triode mode if you run them in triode configuration, which appears to be the case here. And if we look at these valves, we can see they have got really hot in the past. You've got some discoloration on the bases. So is that our issue? Well, let's see if we can do some workings out, right? So the first thing to do, once we've given it our visual inspection, remember we couldn't see any burnt resistors or anything obvious inside the chassis. So the first thing then we do is we take some voltage measurements. And what I've done is we've got V6 and V5. So always counting from the preamp end. 1, 2, 3, 4. This is V5. This is V6. Okay. This is a cathode biased amplifier. So both of the valves are connected to ground through a cathode bias resistor. This particular one, 350 ohms. It actually measures 348, but that's well within tolerance, so we don't worry about that. But when we're taking our voltage measurements, as most of you know by now, we always take measurements on sockets in relation to the cathode, not ground. Now, in a fixed bias amplifier, the cathode is grounded, so they're one and the same thing. But in a cathode biased amplifier, you have to take it on the cathode itself, not the chassis or the ground, to get your actual true measurements. So that's what we've done. So I always put voltage anode to cathode rather than anode to ground. In pentode mode, on each side, 377 volts, 376, close enough. And in triode mode, 379, 376. Okay, so there's a slight difference there, but nothing that caused the hum. When you run in triode mode, what you're doing is you're connecting the screen grid 2, to the anode. So you combine those two together. So we measure the voltages on the grid 2 relative to the cathode. In pentode mode, 381, 379. Switch it to triode mode, which means the screen grid doesn't come from a separate node anymore. It's getting its supply from the anode. 379, 376. Again, close enough. Nothing to worry about there. Okay, let's measure across the cathode resistor, which measures 348 ohms. Our voltage cathode to ground, so we're measuring across the resistor in pentode mode, 35.7 volts, and in triode mode, 35.7. So each side remains the same. So there isn't something weird going on, like an electrode dropping out, for example. Okay, so we can run the numbers on that to see what our dissipation is, but I can see on the oscilloscope that both sides are conducting. All right, so that's our that tells me that each valve is working and they're closely matched enough that this shouldn't be the issue. Okay, so moving on then. So where is this hum coming from? Well, in pentode mode, and what I've currently got is my oscilloscope connected onto both of the screen grids on each side, as you can see, and I'm scoping the output there. So yellow is V6 and purple is V5. And there's a tiny bit of ripple there, but nothing that will concern me. And for those that are interested, these are 10 times probe, so I've got 10 times attenuation on just to protect the oscilloscope itself. Okay, so that's when our screens are, try and get this stable for you, connected to their own node on the B+ rail, as is normal operation. So we call this pentode mode. Switch to triode mode, which will then connect the screen grids to the anode of the amplifier. There's your hum, there's your ripple. And it's equal both sides. Okay, So our hum is coming upstream of the screen node, which is actually, if you think about it, kind of what you'd expect. So now we need to find out the cause of that hum. Now I need to draw out the schematic for this and work out exactly how it's configured. But from what I can work out, the power transformer gets its tap from this capacitor here. I think I'm going to have to work it out. So is that one noisy? Have we got a failed cap in that position? Let's move on. Okay, so I've gone through and I've drawn out the B plus or HT rail, whatever you want to call it, for the Carr Rambler, just so I can get my head around what's going on and how they've configured this. Surprisingly simple, to be honest. Off the power transformer, the high voltage winding, you've got a full wave rectifier, one N4007s, 2 on each side, pretty standard configuration. You've got a 100 ohm dropping resistor feeding our reservoir cap, which is a 51 microfarad 630 volt cap, and it's got two 1 meg resistors in parallel on there just to drain down the voltage when you switch the amp off. Now that cap there is the absolute big one, this monster here. All right. After there, you've got your standby switch, which has a pop suppression capacitor across it. Now, I've tried reading the value and I've tried measuring the value and I can't work out what it is, but there is a cap there. It is this disc cap here. Now, there's no value written on the underside, and I suspect that the glue and the wire is covering up the value on top. So I can't tell you what the value of that is. After there, we have our sensor tap for the output transformer. Then we've got the choke. So we'll call that node A. Node B feeds both the output valve screens and the reverb transformer. We've got a 7.5K dropper to node C, which is for the phase inverter, and another stage, I can't remember. 15K dropper down to the final node, node D, which is 10 microfarad, and that's for your preamp. So that's the HTB plus rail, and the half power switch. All it does is it either makes or breaks the screen supply from node B and swaps it with the supply from node A, which is how they usually run. Nothing too complex there. Now, what I did is, because remember we're getting the hum from here but not from here, I connected up. What I've got is I've got a 47 microfarad cap just on a little test board that I can clip into circuit. So I clipped it across the reservoir cap and it made no difference. Okay, so if that cap was faulty, we would notice a reduction in hum, which we haven't got. Okay, so I know that cap's good. We do the same for the cap on node B. Again, no difference. So at this moment in time, I'm not suspecting a faulty cap. So what do we know about pentode triode modes? Well, as I said earlier, often if the valves aren't perfectly matched or one of them is faulty, then that can cause hum in triode mode. Okay, so the customer had supplied to me a new set of 6L6s. So this is why visual inspections are always important, because we pull V5 out. Remember, we knew it got hot, but all looks okay. We pull V6 out, and it's missing the center pin. So I suspect at some point this valve was inserted incorrectly into the amplifier. The pin broke off. You know, the pins were in the wrong place, and that damaged that valve, although it still does pass audio. Fit the new set of valves. We're currently in pentode mode, just like before, and I'll switch to triode mode. Remember when it used to hum. Ready? the hum is gone. In fact, the amplifier is now even quieter. So just a faulty set of output valves. But what this shows is why it's important to both do a full vision inspection, check your voltages, work out how the circuit works, so you can confirm not only what isn't working, but what is working as intended, okay? Because you can never assume. So I've gone through that process. I've eliminated the filter caps as a source of the noise. I've used my oscilloscope to find out where the hum is appearing and where it's not. I've done my visual inspection. There's nothing burnt inside, but when we remove the valves, we find that broken pin. We see the signs of overheating and discoloration, so we know there's been something going on before. I've confirmed the level of hums on a spectrum analyzer. It's just a cheap iPad one. I can do it with this one as well, but often this is just quicker. And we fitted new valves. I've tested them all. We're up to spec. The noise is gone. We can call that one good. Do you remember before the output sine wave looked awful on the scope? Well, that's it now running. Looks fine to me. Perfectly symmetrical. Nice. Sorted. So, a couple of complaints. Other complaints, sorry. He said there's a couple of pops and bits and pieces. I suspect it was all related to that valve there. But I'm going to leave it soak tested. We'll play test it. He said there's a ghost note sometimes. I've yet to hear that when I've played it. But we'll keep it on the bench soak testing, get this thing nice and screaming hot now, see if anything else appears. It could be an issue with the cabinet itself, so once I get the chassis loaded back in the cabinet, we'll give it another play test, see where we end up. But yeah, all good.